This is our chapter starting acid-base chemistry, and we're going to concentrate on monoprotic acids, which are acids that have just one hydrogen. Acid-base chemistry is really important in kind of everyday application of chemistry. One of the biggest reasons we study acid-base chemistry is because it's such a part of our environment. Our environment has lots of water, and so anytime we put things in the atmosphere like sulfates or nitrates, it reacts with the water in our air to produce things like sulfuric acid and nitric acid to varying concentrations. We call that acid rain, and it can lead to things like forest destruction. It can also lead to things like decay for stone things that we built or metal things that we built, because on the surface of these structures that we've built, it's basically calcium carbonate, or if it's like a metal building, a metal structure, so there's metal on their surface, and when acid rain hits it, there's an acid-base reaction that happens on that surface, and it eats away the surface of the things that we've built, and so we call those things decay, or, if it's metal, we call it rust. Now, the acid-base chemistry isn't just happening on the surface, because our environment can hold so much water, it's relatively warm, and so the humidity can be high. We can have a lot of acid-base chemistry happening within the air when there's pollution. And so that means that the environment is very different when there are those pollutants and kind of an acidic environment than when those pollutants aren't in the air. Now, all these things matter a lot to the people that study our environment, like environmental chemists, and also people like urban planners and architects and civil engineers, people that are designing places for people to live in different areas. So acid-base chemistry has really wide-ranging applications. We should review a few things about acid-base chemistry, some equations and concepts. On this side, we have a picture of a pH meter. And that's just a little reminder that in general, we see the pH scale from going from about 0 to 14. Now, it's possible to get pHs lower than that, but 0 to 14 is kind of our normal pH range. Now, on the low side of the pH range, so anything lower than 7, we're going to call those acids, and anything that's higher, we're going to call those bases, or another word for that is alkaline. Now on this side, we have some equations that have to do with acid-base chemistry. When we're calculating pH, we use the negative log of the hydrogen ion concentration, and we can find that hydrogen ion concentration using a couple different calculations that we're going to practice. If we're going in the opposite direction and we're trying to find the hydrogen ion concentration from the pH, we would use this equation here. So 10 to the negative pH, that's the inverse of this equation, the inverse of log. And there's also a relationship between the hydrogen ion concentration and the hydroxide. They multiply to be the Kw, which is the dissociation constant for water, and that's 1 times 10 to the negative 14. All right, I mentioned that there were a couple different ways to find hydrogen ion concentration, and it really depends on what type of acid you're working with. If you're working with a strong acid, they completely dissociate, which means that for every strong acid molecule you have, you get a hydrogen ion. And remember, this H3O, that's called the hydronium ion, and a hydronium ion is just equal to a hydrogen ion in water. So a hydrogen ion in water and a hydronium ion, those are pretty much synonymous with each other. So in a lot of reactions, if your acid is reacting with water, you're going to get the hydronium ion. We could also have written this reaction like this. That's just taking the water out of both sides. So hydronium and hydroxide are pretty much the same thing. And so when an acid molecule dissociates in water, you're going to get a hydronium ion. And that means that the pH is equal to the negative log of the hydronium ion. So you can write the reaction or the equation that way too. So for a strong acid, for every acid molecule you disassociate, you get a hydronium ion that's completely disassociating. So it's pretty much 100%. And that means that the concentration of hydronium ions is equal to the concentration of the strong acid. And that makes finding the hydronium ion or the hydrogen ion concentration really easy, because if you have the molarity of a strong acid, you have the molarity of the hydrogen ion. So in this case here, the 0.1 molar of a hydrochloric acid is one of our strong acids. To find the pH, we would just say that the pH is equal to the negative log of 0.1 molar. And we don't have to write the molar in there because those square brackets usually indicate molar. And if you do that on your calculator, you get that the pH is equal to 1.0. Now we'll talk about sig figs in just a little bit, but we're really just going for the value here. Now in this second example, we're trying to find the pH of a 0.1 molar potassium hydroxide. Potassium hydroxide is a strong base. And so it doesn't directly give us the concentration of hydrogen ions. What it directly gives us is the concentration of hydroxide ions. But we can get from hydroxide ions to hydrogen ion concentration, and then we can get from hydrogen ion concentration to pH. Now again, because it's a strong base, we know that the concentration of hydroxide ions is equal to 0.1, so that's the same concentration as the potassium hydroxide. And then we can use the equation hydroxide times hydrogen ions is equal to Kw, which is 1 times 10 to the negative 14. If we divide both sides by OH, we would get that the hydrogen ion concentration is equal to 1 times 10 to the negative 14 divided by OH. Now if I clean that up just a little bit, we would do that the hydrogen ion concentration is equal to 1 times 10 to the negative 14 divided by our hydroxide ion concentration, and you would get 1 times 10 to the negative 13 for the hydrogen ion concentration. And then we can use that to find the pH. So it'd be pH is equal to the negative log of 1 times 10 to the negative 13, which would be 13. Now again, those numbers should kind of make sense. We have a strong base, so its pH should be very high. In this solution here, we have a strong acid, so its pH should be low. Now, if you need to be reminded about which ones are our strong acids and our strong bases, we have this table over here. Our strong acids are given here. All of them are monoprotic, except for sulfuric acid, which is a diprotic acid, but it has that little A to remind you that sulfuric acid, losing its first hydrogen, is the strong acid reaction. After that, losing its second hydrogen is a weak acid reaction. And then we have our strong bases here. This quaternary ammonium hydroxide, that's not something that we're going to deal with. These are all bases that you're probably pretty familiar with. They're all alkali metal bases. We've been talking about the pH scale. And the pH scale is based on the hydrogen ion concentration. But there's also a scale based on the hydroxide ion concentration, so based on these concentrations, and that would be called the pOH. The pOH is not a very common scale to use. We use it for calculations, but we don't have pOH meters because most hydroxides are insoluble, and so pH, something like a pOH meter, which would measure the concentration of hydroxide in solution, because most hydroxides are insoluble, pOH meters don't really exist just because of the physical nature of most hydroxides. They're solids, so it's impossible to measure their concentration. But we can use the hydroxide, the pOH scale for calculations, and there is a relationship, just like there's a relationship between hydroxide and hydrogen ion concentration, there's a relationship between pH and pOH. So pH and pOH add up to be 14, which is the log of the Kw. Remember, Kw is times 10 to the negative 14. You take the log of that, and you get 14. Now we say that for pure water, the pH is 7. And the reason why that's true is because the hydrogen ion concentration times the hydroxide ion concentration is 1 times 10 to the 14. And if we're just talking about water, these are in a 1-to-1 ratio all the time because water disassociates to make 1 hydrogen ion and 1 hydroxide. And so you would get 1 times 10 to the negative 7 and 1 times 10 to the negative 7. That's a 1-to-1 ratio. And if this is the hydrogen ion concentration, you take the negative log of it and you would get a pH of 7. So for pure water, the pH should be 7. But if you look at where people live, so this is kind of some data about some locations, the pH, and this is about a pH 7, the pH for most people's water are on the basic side. The reason why that's true is because there's a lot of alkali metals in our surface environment and our soil, and those alkali metals lead to our water being slightly alkaline, which is on the base side. Right. So because this is Chem 5, we're going to talk about how the acid-base chemistry really happens, not just our general approximations that we learn in general chemistry. And where we need to start is by looking at this relationship here. This is true that hydrogen and hydroxide are in a 1-to-1 ratio and that they multiply to be 1 times 10 to the negative 14. When you're in just pure water, or there's no significant acid-base chemistry happening in that water. When acid-base chemistry is happening in the water, and by acid-base chemistry, I mean we have any significant concentration of acid or base, it suppresses this self-ionization of water. So if there are more hydrogen ions in solution, like we have an acidic solution, it forces this equilibrium in this direction, which suppresses this ionization, and it means that by adding hydrogen ions, we shift the equilibrium to the water side, and we overall lower the concentration of hydroxide. And if you need to see that in terms of numbers, if you have a strong acid solution like HBr, and you have a concentration of 1 times 10 to the negative 4, that's not a huge concentration, it's pretty low. You would calculate a pH of 4, and a pH of 4 would have a hydroxide ion concentration of this, okay? And that hydroxide ion concentration can only come from the ionization of water. So that concentration would be this right here. And so in that case, we know since water produces 1 hydrogen ion for every hydroxide, and the water is the only place we can be getting the hydroxide, if this is 1 times 10 to the negative 10, the hydrogen coming from the water ionization is 1 times 10 to the negative 10. So in this case, even a really low concentration of HBr can make water only producing, a much lower concentration than the 1 times 10 to the negative 7 that it would be when it's pure water. Now again, strong acids completely dissociate, and so their concentration has a bigger impact directly on the acid-base chemistry that's happening in water. But weak acids and bases do not completely dissociate and ionize in water, and so their ionization is governed by their equilibrium constant. So for acids, we call them Kas. For bases, we call them Kbs. Now, Kas and Kbs tend to be pretty small numbers, and written in scientific notation, it's a little inconvenient. So we also have this scale called the pKa and pKb scale. The pKa, so that p just means the negative log of something, just like pH means the negative log of the hydrogen ion concentration. But a p scale just means a negative logarithmic scale, and so the pKa is a negative log of AKA. So the smaller the Ka, the bigger the pKa. And when you think about that in another direction, that means that the smaller the pKa, the stronger the acid is. Anytime an acid loses its hydrogen ion in an acid-base reaction, it makes what we call the conjugate base. We also call these things conjugate pairs. So this is the acid and its conjugate base. They are a conjugate acid-base pair. The same thing happens for bases. When bases get a hydrogen, so this one's going to get the hydrogen from that. So when this base gets the hydrogen, it produces an acid, and this is called the conjugate acid. And we can think about the relative strengths of those acids and bases by looking at numbers like their Ka or their pKa. Now we could also look at Kb's or pKb's, but Ka tables are much more common than Kb tables. So let's look at these two examples. We have formic acid and benzoic acid. When formic acid gives up its hydrogen ion, it produces the formate ion, which here is the conjugate base. And when benzoic acid loses its hydrogen ion, it produces benzoate, which is the conjugate base in that reaction. Now when we compare the Ka's for the two acids, so this is formic acid's Ka, this is benzoic acid's Ka, I can see that the Ka for formic acid is higher than the Ka for benzoic acid. So formic acid is a stronger acid. Benzoic acid is the weaker acid. We could have also compared their pKa's. The lower the pKa, the stronger the acid. Now the strength of the acids can tell us about the relative strength of their conjugate bases. The stronger the acid is the weaker base. So the stronger acid makes the weaker conjugate acid. The weaker acid makes the stronger conjugate base. So by identifying which one is the stronger and weaker acids, we can identify which ones are the stronger and weaker conjugate bases. And in this case, it means that benzoate is a stronger base than formate because benzoate comes from a weaker acid, benzoic acid, than formate comes from, which is formic acid. So now that we're talking about how acids and their conjugate bases are related to each other inversely as far as strength goes, I wanted to talk a little bit about, kind of touch on some organic chemistry concepts here to kind of explain why some acids are stronger acids than others. So let's look at salicylic acid here. And when salicylic acid loses its hydrogen ion, so we're looking at this reaction down here. When it loses its hydrogen ion, as an acid would, it has a partial negative charge on these oxygens over here. So this is the hydrogen that it lost. And that partial negative charge can be somewhat relieved by these oxygens interacting with the hydrogen that's on this group. And because it relieves some of that negative charge, it stabilizes this conjugate base. And so that makes it a relatively stable conjugate base. And that means that when the salicylic acid loses its hydrogen ion, it's going to a more stable form than something like the para-hydroxybenzoic acid, which can't have that hydrogen ion. And because it's going to a more stabilized form, it makes it easier for that salicylic acid to lose that hydrogen. And acids that easily lose hydrogens are what we call strong acids. So I'm not saying that salicylic acid is a strong acid. I'm saying that it's a stronger acid than its para-hydroxybenzoic acid kind of comparison. So these two acids have the same molar mass, they have the same chemical formula, but because one produces a more stable base, it's a stronger acid. Let's practice a little bit with some calculations. We are trying to find the pKa for an acid. It's benzoic acid. That is a weak acid. And it matters that it's a weak acid because we can't just say that its molarity is the same as the hydrogen ion concentration. In this case, for weak acids and weak bases, we're going to write an equilibrium table. So my general plan is I'm trying to find the pKa, which means I need to find the Ka, which means that I need to find the concentrations. And so, like I said, we can't just say that the concentration is equal to the original concentration because this is a weak acid. In this problem, it also tells us the pH. The pH is going to allow us to calculate the hydrogen ion concentration, and that's going to allow us to find all the other concentrations. Now, when we set up an ice table, we need to take into consideration the initial concentration, so that's 0.0450, and none of it is disassociated, so we haven't made any of those yet. The change, we're going to use the pH to find the hydrogen ion concentration change. So we're going to use that pH to find what we're going to write right here. All right, so we know that the pH is equal to 2.78, and we know that the hydrogen ion concentration is equal to 10 to the minus 2.78. And so I got that the hydrogen ion concentration is 0.001659. There are some numbers after that. And I'll take all those numbers through, but I'm only going to write out a few here. So I know that because the pH is 2.78, that we produced 0.001659 hydrogen ions. Now we need to use our stoichiometry concepts here. We can see that the benzoate ion and the hydrogen ion are in a 1-to-1 ratio. So if we produced that much hydrogen ion, we produced that much benzoate, and that means that we used that much benzoic acid. So at equilibrium, this is going to be 0.450 minus and these are going to be plus. So now the Ka is products over reactants. And so these are the same. I'm just going to say squared on the top. And then on the bottom. On my calculator, I got 6.35, so numbers after that, times 10 to the negative 5. So that is my Ka, and now I need to get to the pKa. So the pKa is equal to the negative log of the Ka. And when I did that, I got 4.20 on my calculator. Now again, when we calculate these numbers, the Ka tells us about the relative strength of the acid. The lower the Ka, the stronger the acid is. So this is, it's not very low. So this, again, makes sense that it's a weak acid. Now I mentioned that we would talk about sig figs later, and I thought that we should do that now just so that we can go back and look at the sig figs of that last problem. When we're doing logarithms, if I'm doing a logarithm of a number like this, I can really break it up like this. So I'm doing the log of the times 10 portion, and I'm doing the log of this number out front, and then I can add them together. Now the difference between those two numbers, the 2.0 and the times 10 to the 6th, is the 2.0 is a measured number, and the times 10 to the 6th, that just gives it magnitude. It makes it a big number. So out of those two things, only one of them should matter for sig figs. Only measured numbers tell us the number of sig figs. So when I'm doing the log of that, this is the portion that should tell us the sig figs. If I track the sig figs here, 2.0 has 2 sig figs. So if I'm coming down here, this should only have 2 sig figs, which means just the 3 and the 0 count. And so for proper number of sig figs, it should only have 2 places past the decimal. Now let's go back and apply those sig figs to this last problem. The first calculation that we did was this pH calculation here. And using that information about sig figs, the places past the decimal is what determines the sig figs when you're doing the anti-log. So 2 places past the decimal means that this would have 2 sig figs here. So this 6 would be my last sig fig. So I'm going to underline that as I go along. Like this. And then the second calculation that I did is I used these numbers. So I did the subtraction there, and I put that down under the Ka. And if I follow along, it's like this. All right, on the bottom, I'm taking a number with 4 places past the decimal, subtracting out 4 places past the decimal. And when I did that on my calculator, I got 0.43341. And I'm going to mark it to 4 places past the decimal because that's the subtraction significant figure rule. When it's 4 places past the decimal, that also happens to be a number with 1, 2, 3 sig figs. And when I look at this number at the top, it's 1, 2 sig figs. Dividing a number with 2 sig figs by 3 sig figs will get you a 2 sig fig number, so that's 1, 2. And then again, we need to get back to our significant figure rules for logarithms. And what it says is that something with 2 sig figs here, so 1, 2, is going to have 2 places past the decimal, which is what we had. So I'm not going to change the answer or anything like that, but we're just kind of explaining the sig figs. All right, we've talked about the calculation of finding the pKa from a weak acid concentration. There's another way besides Ka or pKa to show how much an acid disassociates, and that's called fractional disassociation. And the way that we calculate it is it's this number here. It's the amount that it dissociates, so that's the anion, so that would be the conjugate base, divided by the total concentration of the acids on the bottom there. Now this is different than Ka because Ka would be the products over the reactants, and if it's products over reactants, that looks similar right now, but if there's multiple products, it's product times product, reactants times reactants. That multiple sign is different than what we have here. So the calculation, the numbers are going to come out different. Now just a little reminder, we use F sometimes to talk about, to be the initial concentration. And where we're getting this F minus X and these X's are basically by doing an ice table. And let me show a little example up here. This is just your basic acid disassociating into hydrogen ions and an anion. I'm going to label the initial concentration as F, and then when we do our ice tables, we would subtract from this side and we would add to this side. So F minus X is what we get at equilibrium. This is X and X added to this side. And that's what we're seeing put in here. For the anion, it's X, so that's on top here. And for the HA, that's F minus X. That's the concentration of the HA. So let's do a practice calculation right down here. It says, what is the percent fraction? So we would take this fraction and make it into a percent for the dissociation of that orthohydroxybenzoic acid. All right, so we know that we're going to have to calculate this. We need to know the concentration of the anion and the concentration of the HA. And so we know that that is X. We're going to use this equation here where the alpha is equal to X over the formal concentration. And to find what X is, we're going to need to use the Ka. Looking back at our equilibrium table, we can see that the Ka would be products over reactants, so that would be products X squared over reactants, which would be the initial concentration minus X. I'm going to bring the work down here. So I have the Ka. It's equal to X squared over 0.05 minus X on the bottom. And when I multiply both sides by 0.05 times 10, or 0.05 minus X, like this, so those would cancel out, I get and if I kind of do the distribution there, times 10 to the minus 5 minus 1.07 times 10 to the minus 3x equals x squared. And I can see that this equation is going to be a quadratic. Now what would have been nice is if we could have said that like x minus x or plus x essentially goes to 0. I don't want to say that here because the Ka isn't that small, so minus x and plus x might actually be significant, which means that we're going to have to solve that quadratic. And to solve the quadratic, I'm just going to clean things up a little bit here so that I have some room. When I rearrange that into a quadratic equation, I got 1.07 times 10 to the negative 3x minus 5.35 times 10 to the negative 5th. So we have our A, that's 1, our B, and our C. All right, when you go through and actually solve that quadratic, I'm not going to show all the work there. You could use an equation solver if you had one, or just use the quadratic equation. I got that x was either negative 0.0078, some numbers, or x was a positive 0.0678. Now we're only going to use the positive number. It doesn't make sense to use a negative concentration. So I'm not going to use the negative part. I'm just going to use the positive. And so that is my x, and I'm going to put that back over here. So alpha is equal to 0.00678, and then divided by the initial concentration, which is 0.0500. And on the calculator, I got that came out to be 0.1356. So that's the fractional dissociation. If I want to make that into a percent, I'm going to multiply it by 100%, and I would get about 13.56%. With sig figs, it looks like I'm only going to have 3 sig figs here, and so it should probably just be 13.6%. There's this little comment down here at the bottom. It says percent dissociation increases with dilution. And that's because as the concentration goes down, the alpha goes up since they're inversely proportional. So ways to talk about the relative strength of acids and bases, we can use Kas, we can use pKas, and we can also use fractional or a percentage dissociation. also wanted to talk about buffers. A buffer is defined as a solution that resists the change in pH, even when we add an acid or base to them. So normally an acid would lower the pH of a system and a base would increase the pH of a system, but buffered solutions resist those changes. A buffer is made of a mixture of a weak acid and its conjugate base, or you could do the opposite. You could actually take a weak base and mix in its conjugate acid. Now, buffers are really important to us because most biological systems need a buffering system so that they can keep their pH pretty constant. For example, in like waterways and streams and things like that, the pH is relatively close to neutral. I'm not going to say exactly 7, but somewhere between 6 and 8 in most kind of normal environmental conditions. But if the water becomes too acidic, bacteria that grow in acidic solutions can blossom there, and those bacteria can wipe out normal bacteria that is healthy for that waterway. And it can also happen in the opposite direction. So like our lungs are slightly basic, so they're slightly on the higher pH side. And one of the reasons why it needs to stay that way is because if our lungs become neutral pH, bacteria that survive, that thrive in neutral pH can start to grow there, and that is not good for our lungs. So by controlling the pH, by using buffers, biological systems can control the things that grow there. Now again, a buffer is made from taking usually a weak acid, something like acetic acid, and adding its conjugate base. So that would be sodium acetate. So the conjugate base there is the acetate ion. You need to put a counter ion there to neutralize the charge, but the sodium doesn't really play a part in this reaction. And why that situation is so important is because, or why that combination is so important is because it creates a mixture that doesn't react with each other really. If the acetic acid reacts with the sodium acetate, it just makes more acetic acid, so it continually replenishes itself. And so this is kind of an equilibrium situation where an acid and a base can be mixed with each other, but they will not go through significant acid-base reactions. And so you have this mixture that can counteract bases. So if you add a base, the acetic acid will react with it and it will make some sodium acetate. So it takes a strong base. You can add something like sodium hydroxide, and the acetic acid is going to react with that sodium hydroxide and make acetate ions. So it takes a strong base and it makes it into a weaker base. And in that way, it reduces the amount that the pH is going to change. It works in the opposite direction too. If we add something like a strong acid like HCl, the acetate, the conjugate base, is going to react with that HCl and make acetic acid. And so it takes a strong acid and it makes it into a weaker acid. And it minimizes the change in pH to the acidic side also. Now this works best when the concentration of the acid and the base are quite high so that it can counteract a lot of strong acids and strong base. So what we call the buffer capacity, so the buffer capacity is the best when the buffer concentration is the highest. And it also works best when there's about equal amounts of the acid and the weak conjugate base. So when there are equal amounts, it means that it has an equal buffering capacity in both the acid and base direction. If there's too much acid in your buffer, it will only be good at reacting with bases. And if there's too much base in your buffer, it will only be good at minimizing the effect of acids. But if there are equal amounts, it can buffer it in both directions. Now, just a little example to show you that it's true that the components of a buffer don't react with each other. I want to do a similar calculation than we just did talking about the alpha, the fractional dissociation of an acid. So before we did the fractional dissociation of a weak acid, and here I want to show you how the numbers play out for a mixture of an acid and its weak conjugate base. Here we have a very similar calculation to the one we just did, finding the alpha for something with a pKa of about 4. So we would use this equation, so x squared f minus x. We would be able to calculate x again, just like we did before, so you'd have to solve a quadratic to do that. Once we found the x, we could put that into our fractional dissociation reaction. This is the, remember, initial concentration is F here. And so as long as we can go through the steps the same way we did in the last problem, we would get that for a weak acid with a pKa of 4 and an initial concentration of 0.1 molar, the alpha is about 3.1%. So some dissociation, but not very much. So we just saw that a weak acid would not dissociate very much in water. Let's talk about what the base component of the buffer would be doing. So the base component would be an anion, and if we did a similar calculation to figure out how much it's reacting with water, we could calculate the alpha. So we're going to go through the same steps there. We would do an ice table, we would use the Kb, and so we have the pKb, we could go to the Kb, and then we could use that Kb to find x, just like we did here. It would be a quadratic just like it was before. So the anion that's in solution is not making very much of the conjugate acid. So it's not making much acid. And what that means is that we have kind of the acid is not making much conjugate base, and the conjugate base is not making much acid. And really what that means is that you can get a mixture of these two things where they are not reacting with each other or with water to make many products. So we're not getting much products there, but even if they did make any products, they would be remaking more of each other. So again, just some numbers to show that the reactions between an acid and its conjugate base are relatively minimal, and that's one of the reasons why a buffer works so well. Now in your general chemistry, we basically just told you that these numbers were relatively small, and because those numbers were relatively small, we can do some approximations, and that approximation came out to be an equation that was called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation allows us to calculate the pH of a buffer if we know the relative concentrations of the acid, the weak acid, and its conjugate base. When we were talking about buffering capacity, we said that then when the base concentration and the acid concentration were equal to each other, it had equal buffering capacity in both directions. What also happens in this situation is if these are in a 1-to-1 ratio, this whole thing goes to 1, and the log then goes to 0, and the pH and the pKa will be equal to each other. So kind of in that one situation where we have equal amounts of acid and its weak conjugate base, the pH of the buffer is going to be equal to the pKa of the weak acid. So let's do a little calculation of how we would prepare a buffer. This problem says calculate the milliliters of potassium hydroxide that should be added to 5 grams of MOBS. So MOBS is a weak acid. It has a really crazy kind of name. There's a reason why we abbreviate it MOBS. It's actually like morpholino-propensulfonic acid or something like that. And I don't expect you to know what MOBS is off the top of your head, but there are a couple charts at the end of the slides that go along with this video that would tell you what MOBS is, and it also gives the formula weight, and it says that the pKa of MOBS is 7.48. 0.8. Okay, so that's information that we would actually have to look up. So we're going to add our KOH to this 5 grams of MOBs to give a pH of 7.40. Now, just a little reminder, we're using the Henderson-Hasselbalch, which tells us that the pH is equal to the pKa plus the log of the conjugate base over the acid. So in our problem, we're given the pH, we're given the pK, either looking it up or in this case it was given, and we need to be able to find this ratio, and that'll allow us to calculate the milliliters of KOH. To find that ratio, part of it is we can use a stoichiometry calculation to go from grams of MOBs to moles of MOBs, and that's our weak acid, so that's going to help us out on the bottom. So I'm going to do that calculation first. So 5 grams of MOBs, and it's formula weight. So formula weight is the same thing as molar mass. And I got 0.0223, and then I think there was a 9 after that, moles of MOBs. Remember, that is just the initial. We know because of ice tables that we are going to use some of this to make the conjugate base. So we need to do the initial concentration minus X on the bottom there. That's going to be our equilibrium concentration of HA, and then the equilibrium concentration of A is going to be how much we took away from that weak acid. So if I fix up my Henderson-Hasselbalch there, I'm just going to write this. pH is equal to pKa plus the log of X over F minus X on the bottom. But the good news is the problem gives us the pH and the pKa, and we just found X. That's our initial concentration. So we have this here. So the only thing that we're missing is these X's. All right, so I'm gonna solve for that over here. The pH was 7.40, the pKa is 7.48. Like this. The first thing I'm going to do is I'm going to subtract 7.48 from each side. Now that last one, I could see that I put in too many 2's there, so I'm just correcting this. This should be 223 minus X. I think I accidentally put in too many 2's the last time. Okay, so the next thing that I need to do is I need to get rid of this log. And to do that, I take the inverse log, which is 10 to the power, like that, of each side. And when I do that, I get 0.8317, so numbers equals . Okay, and then I need to get rid of these things that are at the bottom, so I'm going to multiply each side by that. And when I did that, I got 0.01854 minus 0.8317x equals X. All right, and so rearranging that, I got 0.01854, and I just moved, I added this to each side. And now I'm just going to divide each side. All right, and I'm running out of room there a little bit, so I got 0.0102 is equal to X. All right, and so that X is equal to my my conjugate base there. So that's going to be my hydroxide ions. And now that I know how many moles of hydroxide ions I can tell how many milliliters of this potassium hydroxide I'm going to need. So I'm just going to clean up all this algebra here at the bottom so that I can give myself some more room. And I'm just going to do that last stoichiometry step. Okay. So I need to provide 0.102 moles of hydroxide. 1 mole of hydroxide, I need 1 mole of KOH. My KOH is 0.626 moles per 1 liter. 1 liter is the same thing as 1,000 milliliters. And so moles cancel with moles, and I get milliliters, and I got 16.3 milliliters. So that's actually 16.2 milliliters. Right, so that is how we would basically make the recipe for a buffer. We would put 16.2 milliliters of the KOH, and we would add that into 5 grams of the MOBs. Now when we did this recipe, this kind of calculation, we're basically just trying to figure out what ratio we would need the acid and the base to be in so that we would get a very specific pH there. But that doesn't take buffering capacity into consideration. Remember, buffering capacity is best when there's equal amounts of acids and bases. And in that situation, it means that the pH would be equal to the pKa of the acid. So when you're trying to make a recipe for a buffer and you know what pH you want it to be at, you want to pick an acid that has a pKa that is as close to that pH as possible. Our pKa here was 7.48. That's pretty close. Okay, so that was a good choice. But even with just that 0.08 difference, if we look at the amount of acid compared to the amount of base, and I know that the amount of acid is actually F minus X there, so it was 0.0223 minus 0.0102. And so when you do that, you can see that the acid and the base are pretty close to each other. So in this situation here, because we were able to pick a pKa that was equal, we picked an acid that had a pKa that was close to the pH, we were able to make a buffer that had almost equal amounts of acid, so of base up here, and the leftover acid at the bottom. And that means that we were also able to make a buffer that would have a high buffering capacity in both the acidic and the basic direction. But it also, if you're not able to pick an acid that has a pKa close to your pH, you'll be able to make the buffer, but the buffering capacity of that buffer is not going to be great in one direction or the other. So as we were just saying, the maximum capacity to resist pH change in both directions happens when the pH is equal to the pKa. So that means that the acid and the base would be a 1-to-1 ratio with each other. There's this number that we can calculate called the buffer capacity. The buffer capacity is a calculation of how much the concentration change, so how much acid or base you can add to the buffer solution, and how much the pH is going to change. Now again, I said that ideally we try and find a acid to make our buffer with that has a pKa that is equal to the pH of the buffer that we're trying to make. But that's not always possible. So kind of a more useful general way is that we try and find a acid that has a pKa within 1 pH unit of the buffer that we're trying to make, which means that we use lists of acids and we kind of pick from a catalog of which ones we want to use. And these are some slides that are kind of added on here. I just pulled these out of the book. These are a bunch of acids and their pKa's. So when we were doing that problem before, I used MOBs, which is this one right here. And so since we were trying to find trying to make a buffer with a pH of 7.4, that one was the closest to the pH that we wanted. So the pKa was closest to the pH that we wanted. So in this video, we did a little review of acids and bases. Our acids were monoprotic acids. We talked about how you can go from pH to concentration, concentration to Ka, Ka to pKa, and also back the other direction. We talked about fractional dissociation and how that's another way to show what's happening to an acid or a base in a reaction. That led us into a little review of buffers, and we did a practice calculation about kind of making a buffer recipe, and we talked about buffer capacity.